Viral Shah, co-founder and CEO at Julia Computing. Welcome back to the Data Exchange podcast and what hopefully will be the annual check-in with the Julia world.
Fantastic. Great to be here, Ben. And I always enjoy speaking with you. Looking forward.
All right. So first, let's get this off the plate. Julia Computing, your company, raised 24 million Series A. So I guess the big question, Viral, is what are your plans for your Series A?
It's always hard being an open source company to figure out what your path to market is and what your plans are, right? So for those of your readers who've been following our journey, we actually raised our first seed round in 2016, and we took our time and, we've been patient with figuring out what's the right, business model, and only then sort of raised the venture capital, right? Because Julia is really dear to our hearts, and we have to sort of do the things in the right way. So we finally feel like we've figured it out now, right? So, over the last few years, the big milestones have been that Julia went to 1.0. Enterprise adoption has really taken off. The Julia data science ecosystem is beginning to sort of like be, really better than anything in the Python and R world, at least performance-wise. And the Julia scientific machine learning ecosystem and many of these tools are just phenomenal. So we figured out, as we were beginning to engage with customers over the last few years, we realized that there are two things that we're going to do. One is build a cloud platform to run, the best cloud platform for running Julia on the cloud.
Awesome.
AWS, Azure, or GCP, right? So that's Julia Hub.
That's
okay.
Awesome.
And then the second thing is, we really, Julia gives everyone superpowers, right? Like it's so good, so fast, easy to use, solves the two-language problem. So we want to use Julia to build industry-specific solutions, and we actually just released Pumas in partnership with Pumas AI, and that's something that runs on Julia Hub. So I'll pause here. Julia Hub as a cloud platform, and then domain-specific solutions is the way we're building out a business.
So I also noticed that there's now, you can now, or how to phrase this, somehow it's now easier to run Julia on SageMaker, right? So that's Amazon. So that's validation from Amazon that the people were asking them about it, right?
No, it's everywhere, right? I mean, Julia users have been asking Microsoft to add it to Azure Notebooks. People have been asking Google Colab. People have been asking SageMaker. People have been asking Binder. I mean, Julia is everywhere, right? It's an open source tool, and we want it to be. It's on REPL.it. Replit. I don't know how do you pronounce it.
Right.
Yeah, but it's everywhere. I mean, that's real validation of the ecosystem growing.
So what would be so without if feel free to not share proprietary information. So what would be an example of a vertical specific offering?
Yeah, actually, Pumas is the one. So, Pumas AI is one of our partners with whom we have co-developed this software called Pumas, which stands for Pharmaceutical Modeling and Simulation. And we just announced Pumas 2.0. It is cloud only. Pumas Enterprise is cloud only. And it's under installation at a dozen pharmaceutical companies, all the big fancy logos, that you can imagine.
So is the Julia itself, or are there special packages for this vertical, or so what makes it vertical specific?
So it's so what happens is that we install Julia Hub, which is a broad and generic platform. So it comes with VS Code. It lets you fire up VS Code in the browser. You got your Julia environment. You got all the packages, all the package server, all of the usual Julia things. And then in addition, there is this domain-specific package called Pumas. So what the Pumas user gets is, the specific library for working with pharmaceutical models, for simulating them. We have UIs, automatic report generation, but then you can pull in, Julia's data frames to analyze your data, or Flux to do deep learning on the pharmaceutical data, or plotting, or all of the other things that the Julia ecosystem provides. So that's the way, the first domain-specific application is structured. The second one is actually Julia Sim that we are working closely on at Julia Computing. We announced it at JuliaCon. And Julia Sim is a modeling and simulation framework for engineers. So if you were designing the next battery, or you want to figure out how it's going to interact with the motors of your new electric vehicle, that's the kind of thing that you'd use Julia Sim for. Again, it runs on Julia Hub, right? So and it's a supercomputer on the cloud, right? You press a button, you can launch 1,000 nodes, distribute your job, use GPUs, all of the above.
So for some reason, I had it in my mind that the natural vertical would be finance.
Finance is still a big vertical for us. So a lot of users are using Julia in finance. We do not have a domain-specific solution yet. We are working on it. We are thinking about it. We are talking to people. We actually have published a meta language for finance. It's called.
So Viral, for you guys to decide. Okay, so I'm going to choose finance over whatever retail. What's the criteria for you to start investing in that vertical over another?
Well, the number one criteria is, is there a real business that we can build here, right? And the way to build a real business in a vertical is, what are people using today? What is the pain point? Can you provide something that is 10x, 100x, maybe even 1000x better, and take away that pain point, right? Which will make them want to pay. So in the pharmaceutical industry, we found that a lot of the tools used today are Fortran tools, and there was just a real, opportunity to get in there. Similarly, in engineering, we found that people are using decades-old tools. Finance tends to be a little bit more with the times, but there is a lot of room there for new and.
So it's not necessarily that this vertical they're already aware of Julia, or there's a groundswell of Julia in this vertical. You can go in and conquer a vertical with a brand new language. It sounds like. Yeah,
absolutely. Yeah, absolutely. And we find that modeling and simulation has a lot to offer, and that's sort of the direction that we are taking right now. Irrespective, every industry is using Julia Hub, right? And Julia. So, if you have 100 data scientists, thousands of data scientists, you want to work with the data, you want to collaborate, you want to have notebooks, you want to publish reports, all of that, we make it really easy with the cloud security, with the, with the scalability, with all the things that Julia users expect. And so that's sort of, across the board, but then there's a couple of verticals where we have something more.
So in the ML world, you've got kind of these new startups building or kind of hardening and completing kind of the ML ops tool set. This could be like experiment tracking, experiment management, model governance, feature stores. So do you anticipate having, or maybe you can just plug into some of these other tools as well?
That's our view, that we would plug into tools like SageMaker for doing something like that. There is a lot of competition in that area. And, we strongly believe in purpose and mission, right? What is it that we are good at that the rest of the world is not good at?
That's awesome, yeah.
Right. And so if someone's doing other things, I would rather partner up with them and, just make it a partnership and go to the customer gets the best thing, right? They get the best ML ops tool or the experiment tracking tool and the best of Julia from us, right? I don't want to go ahead and build something that other people are much better at doing. So it really comes down to purpose, focus, mission. And our mission is to work on Julia and improve scientific modeling and simulation in ways like no one else can.
So is this in my head, when I think of Julia, there's 3 buckets of users, and correct me if I'm wrong, and this could be like a Venn diagram as well, right? So you've got people who use Julia Core, the language.
Yes.
People who build packages.
Mm-hmm.
And then before, that's all that in my head. And then recently I started to realize there's actually a third bucket, which is like sub communities, like there's a big SciML community, for example, right?
Yes.
So is this the right description of the Julia community?
I think that's a pretty good description. There is, of course, a fourth thing above, which is just the general Julia user, right? Who's combining the basic packages and doing things. But yes, that is a very, very good articulation of what the Julia community is like. What is interesting is that there are many more sub-communities in Julia than you'd see in some of the other.
Yeah. So what are so the sub communities are SciML, Flux, right?
That's
So for
right.
those who don't follow Julia, describe these sub communities.
Yeah, so one of the interesting things is that because Julia started out on GitHub, a lot of our communities also formed on GitHub. So there are over 100 GitHub organizations that are, specific to Julia sub-communities, right? Each organization is a Julia sub-community in some sense. So we have, you already mentioned SciML. Excuse me. So SciML is our scientific machine learning sub-community, which has all of the differential equations and solvers and all of that. Flux is our deep learning community.
And what's the relationship of Julia computing to these sub communities?
Some of these we are actively participating. Like the Flux is we created that sub community in Flux, right? SciML is something that was created more at MIT, but we are now participating in a big way in it. And there are just so many more. It's just kind of hard to articulate every single one.
So when do a group of people in your mind become much more of a formal sub community?
Well, I mean, it's a decentralized community out there, right? So anyone can create a sub community, but in my mind, it becomes something real when you have a body of packages that defines the output of that sub community that turns out to be interesting to the larger community of users, right? So an example could be there's a package called Camellia, right, which is our work on chemistry, computational chemistry, and there are a few packages out there now that are best in class, and now other chemists are beginning to look at it. So now there is a sub community in chemistry forming, and then they come together at JuliaCon. They have a birds of a feather session. So I think once you start seeing sort of some of these activities come together, pull requests, people sort of adding new packages, that's when I think it becomes a real sub community. But I think like a very clear indicator is when they have a cool logo. When a cool logo shows up on the GitHub board, you know that it was worth making that logo.
By the way, at the last JuliaCon, I was struck by how many SciML talks there were. So set aside SciML. So what were the big sub communities represented at JuliaCon?
Oh, that's just beginning harder and harder to track. So Chris Rakokas has done a fantastic job with SciML, and there were tons of SciML talks. I think there were at least a dozen this year, if not more. But I'm seeing sort of a lot of community. I'm seeing two things, right? I'm seeing new professional communities pop up, and new academic communities also pop up at JuliaCon. This year we had over 300 presentations, and it was a complete chaos to sort of put it all together as a purely online conference. But the committee and the contributors did a fantastic job with that. But you're putting me on a spot here. I'm trying to think of what are the other sub communities. But like I mentioned, this chemistry one, right? That was a new one that came together, being led by researchers at Carnegie Mellon University. So the organization is called Camellia. The package is camellia.jl, and there's JuliaChem and all of that stuff. There's a fantastic community in BioJulia, to work with genetic data, for example. There's a great one, like a traditional strong community is JUMP, right? Optimization.
Right.
And JUMP has its own conference called JUMP Dev, but we co-located with JuliaCon this year. So there was one whole track for 3 days on just JUMP talks. And there were talks on like electrical grid optimization, designing new batteries, vehicle charging, renewable energy, all of these things, right?
That's funny because isn't JUMP owned by SAS now?
No, that's actually a different JUMP, right? So JUMP is a company that is, a SAS related thing.
Yeah.
Julia, the JUMP refers to Julia for Mathematical Programming.
Oh, I see.
Project.
I wasn't aware. Speaking of JuliaCon, so the core team of Julia, the people behind Julia gave a State of Julia roadmap, right? And yes, you were one of the presenters.
Yes.
So you yourself specifically called out linear algebra, and then you said something that caught my attention. And I don't know if you were just speculating or it's just concrete. You said something, and forgive me if I'm misquoting you, right? So is it something along the lines, do we need at this point a native Julia BLAS or LAPACK?
Mm-hmm.
Is that an accurate quotation.
Yeah. That is. I did bring up. We have been sort of struggling with all of the BLAS and LAPACK library in Julia, especially BLAS. LAPACK not so much.
Yeah.
Because of architectures and everything is, so many new, types of CPUs are coming out every day. And
so Viral, for our listeners, BLAS basically is the I hate to use the word, but it is legacy linear algebra library, right?
Yeah, it stands for basic linear algebra subroutines.
Right. And basically, under the hood, it powers a lot of things that the data scientists use day to day, right? So
all the machine learning, TensorFlow, PyTorch, Julia, R, Python, everything, NumPy, it's all.
And so why has it never been? Why has no one bothered to rebuild it somehow?
It's really hard, right? So, the people who are best incentivized to build a good BLAS library are CPU vendors. So Intel has MKL and AMD has their own, and IBM has had their own over the years. Cray has had their own. And therein lies the problem, right? They only want to build a good one for their architecture. If you run into a bug, good luck. Unless you're a big paying customer, they're not going to pay attention to you.
Right.
So the open source BLAS libraries don't tend to be as good as the commercial ones. Like, they might not be as good at threading. They might not be as good at like some other things. So, but the biggest problem is composability, right? Because BLAS is multi-threaded. So Python and R, for example, have never been multi-threaded. So this never was a problem for them. Julia is a multi-threaded system. So now as a Julia user, you're writing multi-threaded Julia code, which is calling multi-threaded BLAS code. And now all the threads are sort of stomping all over each other because they're written in two different threading systems. And Julia has a composable threading runtime, right? So if I write a Julia package, you write a Julia package, both are multi-threaded, it will cooperate. But if if we call BLAS, which is not written in Julia, our threads don't know about the operating system's threads or BLAS threads. And so you end up with oversubscription and you lose performance. So you have to then carefully say, I'll give some threads to you, some threads to you, some threads to you, and it becomes hard to program. So this is really why we need to, build from the ground up an architecture, neutral, multi-threaded, high-performance BLAS, and it is a very tough problem. It's a very tough problem.
Is that something that a single entity can take on, or is that going to have to be a cooperative undertaking? So the disadvantage, of course, with a cooperative undertaking, it's going to be slower, right?
I think it has to be someone has to take the lead on it. One entity has to take a lead on it, but it has to be a community effort just because of the vastness of the work that is involved in there. Julia Computing has done a tremendous amount of work, in the compiler and some of the early libraries that will form the basis of a new Julia BLAS. So, fingers crossed. I think it's going to come through.
So the other thing that caught my attention in your folks' keynote is the number of packages reaching 1.0 version status, and in particular for data scientists, kind of the data capabilities, around, for example, some of the packages that you folks highlighted it's maturing are data frames, right? So, and then I guess the CSV package is close to that status as well. So talk to me about the packages for data scientists and how far along they've come over the past year.
So the data frames and CSV are two of the major packages that went to 1.0, and Julia's CSV reader is actually multi-threaded. So it's one of the fastest CSV readers out there compared to what you can get in many of the other languages.
To our listeners, my pet peeve is we need to kill the CSV format, but that's a separate question. We all still have to deal with it. So we need something fast.
So what happens is that the CSV package written by Jacob Quinn, right? Because Julia is a compiled language, it can examine the data types in your CSV file and generate a custom compiled parser and reader for that CSV file, right? And so if it'll take a little bit of time to compile, but then it will scream through your entire data set because now it's compiled through, right? And that's what makes it really fast. and then it will sort of thread it and do all those things. The data frames package in Julia also has been multi-threaded now, and it's one of the top performing benchmarks, top performing packages on the data frames benchmark that H2O.ai put together. I'm sure you're familiar with it.
Right.
So Julia does very well on those. So for data, for data scientists, a way to load your data, a way to play with it. We also have the Parquet readers and HDF5 and all of these other formats, and we're collaborating with everyone to make them even better. But the basic data science workflow in Julia is really good. The plotting libraries have all taken shape, basic plots with plots.jl, or really fancy 3D things. You could use Mackie, which is another package that has really taken off. Good old packages like XGBoost and all are always around. The Flux ecosystem for deep learning. So traditional as well as modern machine learning. I mean, this is the right time to jump in. Like everything that you wanted is available at your fingertips.
Yeah. And the main thing to emphasize here is that, when you're doing machine learning or data science or analytics, you're really talking about a pipeline, right? So you need to compose a few operators in a DAG, basically. And so you want these operators to be as interoperable, as integrated as possible. Ideally, the data interchange between the operators will be as fast and as efficient as possible, right?
Yep.
And it sounds like you folks are starting to get all of the key building blocks in place.
Absolutely. And you made a good point, right? That we really do need to move away from CSV and Julia, because you can have complete control over your memory layout. You can actually work with bit level data in Julia, and so Julia is just really good at working with highly compact, natively packed data sets. And you can just map them completely directly into Julia and then just screen through them. So all of those data interchanges, so we have a very good integration with Arrow, right? For example, we have a very high performance integration with Arrow to pull data, work with it, be interoperable with everyone else.
So what do people in the Julia world do for workflow management and orchestration? So what's the equivalent of Airflow or Prefect or something like that, if you want to manage something and look at status and whatever?
So the tool that is coming together for that is this tool called Dagger, which is which works on DAGs, Dagger.jl. It was originally written by Shashi Gowda, who's now at MIT, and also now being continued by Julian Samaru at the MIT Julia Lab. And it lets you sort of, I would say that it's closer to something like Dask in some sense, in terms of sort of articulating all of your Julia,
So you need, so for something like this, you need like a scheduler, an executor, some kind of metadata store so that you can see the status of things, and then a dashboard of some kind, right?
So some of the dashboarding and things are in early development stage on Dagger. So a lot of the focus has been on getting high performance parallelism and having a very good scheduler. So that's where the work is focused right now. We have some internal tools on Dagger to be able to sort of articulate, being able to see sort of the performance gaps, right? Like, hey, the CPU was busy at this time and was sitting idle waiting for someone else to give it a job. And so those kinds of visualizations are actually in place in Dagger. I don't know if they've been published open source just yet, but I think it's all coming. And I would maybe take this opportunity with your podcast to invite some of your users to try it out and maybe also become contributors to Dagger.
So you mentioned something early on as we were getting started about the need to identify what you're good at and basically double down and invest and grow that market. So, which brings me to a keynote at JuliaCon by Sumit Chintala of PyTorch.
Yes.
Yeah. So he talks about some of the choices they made for PyTorch. So, for example, one of the things that he mentioned, which reminded me of what you said, is early on they realized, look, we can't possibly conquer everything all at once. We need to choose kind of our sweet spot. And so the sweet spot they chose was ML researchers, right? So
Right.
because TensorFlow obviously was already in the market and doing a lot of things, and but they felt like if they can just do well by the ML researchers, that would be a good start. And of course, it turned out to be more than a good start, because then they ended up basically becoming the dominant deep learning framework. So in your case, it's not, you called out simulation and mathematical modeling, right? So is that right?
Yes. Yes.
Yeah. And so who are these people, and are they mostly in academia, or are they also in industry?
Actually, it's mostly in industry and somewhat in academia, right? So academia tends to be at the research end of things, whereas industry is at the, is using it for developing new products, right? The broad modeling and simulation market is $10 billion in ARR today.
So give us some examples of things that involve these things that are kind of things that people would be surprised that what they're not using machine learning.
So there is a huge move towards bringing machine learning into modeling and simulation, and it turns out that in many cases you can speed up your simulation by a factor of 1,000 or more by using machine learning tools. Only when the training time is small enough and you have to rerun the same thing over and over again. So
reinforcement learning, I think, is being used in some cases, right?
Reinforcement learning is being used in some cases, and that, but the problem with reinforcement learning is that it's very expensive, right?
It's computationally expensive. Yeah.
Computationally, it's an amazing technique. It's a very hard technique, but if you figure it out, right? If you crack
it's very hard to actually think through the setup of the problem. What's the reward? Do I have the right simulator? So there's actually a lot of. But let's say if you get to that point, then maybe
reinforcement learning is great. So there is a fantastic reinforcement learning framework in Julia called AlphaZero.jl, which implements AlphaZero in a few thousand lines of Julia in a way that is very easy to work with. Again, driven by a different researcher at Carnegie Mellon, Jonathan. But to your point, the modeling and simulation, has been largely people have used tools like ANSYS or Modelica or Simulink or MATLAB or Cadence or Synopsys in the case of circuit simulations, or tools from companies like Certara or Schrodinger's one of the newer ones in chemistry simulations, right? So there is a series of modeling and simulation tools out there. My estimate is
there's a lot of applications. For example, staffing, logistics, right? So optimizing your factory floor.
Absolutely, right? I mean, like or optimizing railway cars, right? For example, right? Like a schedule. How do you send solving linear programs, right? For example, the traditional use.
So then the idea there is what that because basically. The vendors you mentioned, they have their front end, they're inside these companies, right? So and some of the people who use their tools may not necessarily be programmers, right? So they're using the front end of these tools. So is the idea Julia would be a part of the back end of some of these tools, or what?
Well, actually, we are building our own front end. So what is happening is that scientific machine learning, especially the Julia SciML world, is redefining the way modeling and simulation can be done and really pushing on the boundaries, right? So we have a project with ARPA-E to bring machine learning to engineering simulation. And, with our partners at Mitsubishi Electric Research Labs right here in Cambridge, we demonstrated that we can simulate the cycle model of an air conditioner 500 times faster, using some of the Julia SciML tools. And that's immense, right? Because now the researchers are able to simulate a building for over a year as opposed to just over a week. And that means they can model climate change, the effect of climate change on how the building design and air conditioner design has to work. I mean, the world around us is changing so fast, right? That only through modeling and simulation can we figure out what is the right intervention in terms of what are the right products to build, how to change our designs, how to emit less carbon, and so on and so forth. And so we are seeing this immense opportunity in what is otherwise a very large market, but is rapidly going to, double or triple in the next, 10 years. It has a lot of revenue attached to it. And the programmers, you made a good point. Are they all GUI users? In the past, engineers were GUI users, right? Because they were never taught programming. Today, the people graduating from MIT, Stanford, Cornell, Berkeley, they're all graduating with programming, right? All the engineers know how to program. So what they want is a tool that can go in both directions, right? That take a program, generate a GUI out of it, or if I edit the GUI, I want the programmatic representation back. So all of our tools are two-way programs. We can go from the GUI to the code and back so that people can work with abstractions that they are comfortable with.
Now, there's also simulation, but also more broadly optimization, right? Which I think just about any kind of business unit is doing some kind of optimization, right?
Everything in business is, everything is optimization at some level.
Look, even some analysts are using Excel solvers, right?
Oh, it's been, very widely used in Excel for the last 20 years, right? I mean, so Jump is our, major ecosystem for optimization, right? Where people solve very large and complex optimization problems. And I mean, Jump has its own following and community. I would urge the listeners to check out the Jump dev track at JuliaCon to see all of the amazing applications of optimization in Julia. I mean, and if you think about it, I mean, deep learning is basically an optimization problem. And I have a very interesting point to make here that I think everyone might be interested in is this concept of differentiable programming. I think we spoke a little bit about it the last time,
right.
And I'm thrilled to say that we've come a long way since then. And if you think of optimization, right, what is it basically under the hood, right? You're calculating the derivative, and then you're taking a step in the direction which optimizes your loss function, minimizes your loss, for example, right? So the key is to compute derivatives. And today, Julia has differentiable programming as part of the ecosystem, right? And we have a huge ecosystem of chain rules and things like that, where you can automatically compute derivatives of lots and lots of mathematical functions.
Well, you've had automatic differentiation for a while, right?
We've had it for a while, and it's all about sort of growing the capabilities of that automatic differentiation system so that you can apply to more programs and to larger programs and reduce the compile times and do all of that. Also, a major new development is incorporating GPUs into that process.
So actually, when we were talking about simulation, I guess I was reminded I actually advise a startup that's doing RL for simulations. So they're using Ray RL lib in the backend, but then they plug into they work with the software vendors that you described, like AnyLogic. I don't know if you're familiar with them.
I'm not familiar. Sorry.
Yeah. So anyway, so they plug into that, and then basically the AnyLogic user is still using the any user front end, but then now they have access to deep reinforcement learning at scale. So which means that they can on paper they can handle more complex scenarios and optimizations.
Okay.
Yeah.
That's really cool.
So what about mathematical modeling? Is that a business? Is that something you're seeing in business as well?
You mean broadly mathematical modeling in terms of?
In terms of differential equations.
I mean, we use differential equations for all of our business, right? Like our entire pharmaceutical modeling and simulation Pumas package is built on differential equation solvers. When I was describing that application with simulating the air conditioners, right? The air conditioning cycles, that's all differential equations under the hood.
So Julia Computing then, if you guys can execute and conquer this kind of mathematical modeling, optimization, and simulation world, that's a pretty big market.
That's a pretty big market, and very few people are paying attention to it in terms of vendors. And there are, my count is about 5 to 10 million users, depending on how you count them, who care about these tools. and I think we are best positioned to make it happen.
So you raised the Series A, which means that you can, you know, some of the things that you couldn't invest in, you can invest in. So, but beyond that, so what are some of right now? What are some of you would say, and feel free to pass if you don't want to reveal any secrets. But what are some of your what you would say key blockers, for example, to expanding Julia open source?
Oh, I mean, I will tell you that, nothing secret there. We actually operate very openly, even as a company. And, the business model is very straightforward, right? Like I said, make Julia Hub to be the best cloud environment to run Julia. That's only useful if there are more Julia users out there, right?
Right.
And our estimate is there are about 1 million Julia users out there. And, probably a quarter.
This damn Python people, which I'm one of them as well, are
Python
just
is
are
fantastic.
just dabbling, you know.
Python is fantastic, but it only takes you to a certain level, and there's always
Just that the Viral, the ecosystem of libraries, right? Which actually, honestly, it's good and bad. So it's true that you have a lot of libraries in the Python ecosystem, but it's also kind of a mess, honestly, because basically once you have something working and set up, and then something gets updated, a lot of things can break.
we've designed our package. We learned from Python's challenges in the early days, and we designed the Julia package manager
Yeah.
to avoid those kinds of problems, right? So people really love the Julia package manager today, and
But for example, in the machine learning, so you want to increase the number of Julia users. So what would be the natural population to do that?
um the natural population is basically, like I said, we are at 1 million Julia users, right? Roughly today. What does it take to get to 2 million or 4 million or 8 million, right? Those are the key
Right.
next steps. And for us, what we've realized is that we generally don't pick a sub community. Like, we don't want to target statisticians or biologists or physicists, right? Because then that ends up being about, do I have this package or that package, and so on and so forth.
Right.
So the way we've built this so far, and I believe strongly that is the way to go forward, is to improve the quality of the compiler, the quality of the tooling, the quality of the ecosystem, so that a new user, when they come to Julia, it's easy to learn. They get good compile time, error messages. They get fast compile times. They're able to compile binaries of their programs and deploy them all the way from your big servers on Amazon to
But
guys.
does that statement assume a certain level of sophistication? And by that I mean, the one of the reasons Python is big is that basically anyone can use it. It's fairly accessible, and by that, by anyone, I mean people who don't care about performance.
So Python started out its life as a general purpose language that was fun to learn programming with, that was very flexible. Performance was not the goal.
So I guess what I'm asking you is if you're targeting performance, which actually is a big deal. So when we do surveys and we ask people, so how do you pick these tools? And performance and tuning are quite important to people, right? But
I mean, performance is money, right? Like, everything is running on cloud, and why would you not want something that is 100 times faster, right? That's 100 times less money that you would spend.
So your thesis is if you improve the core language, they will come.
That has been our experience all along, because if we improve the core language and ecosystem tooling, then the packages get that much better, right? So I'll give you an example, right? Like, we added multi-threading a few years ago, and data frames got multi-threaded, CSVs got multi-threaded, differential equations got multi-threaded, and it enabled a new kinds of applications in finance, in climate, in all of these things, right? And so it's you have this lever, right, where by making very small and specific and meticulous changes at the core, the ripple effects can be pretty dramatic and impressive. And that's the path we are going to continue on, and the community will build on top of that, and companies will come because the community is there, and so on and so forth.
Right. And so then so
I'll say one more thing, right? On performance, right? Remember that every time you run a slow program, you're emitting more carbon dioxide than you should.
Right.
It's a moral problem now.
Right. But then I guess I still go to the persona of the person of the as you grow. So right now, how would you describe Julia users? Are they much more sophisticated? Are they much more
The typical persona of a Julia programmer, of a Julia user, is a technical computing persona. So anyone who wants to do any form of applied mathematics or statistics or data science or machine learning, right? You typically, the person who you're not going to get is the person who's trying to design a website, or person who's writing a web server, or a person who is building a distributed system, right? Or a cryptocurrency, for example. I mean, all of these are possible in Julia because the general language, it can do all these things, but those technical communities have a lot of the libraries and tooling available today, right? Like in a pharmaceutical company, in an engineering company, in a circuit design company, right?
But the biggest slice of growth, the big area of potential growth, which might be somewhat challenging, is ML, right?
We are doing pretty well in ML. I mean,
how would you describe your ML community, and how do you get more of them?
So you actually pointed out the SciML subcommunity in Julia, and that has been our focus. So we're doing two things in ML, right? One is making Julia first-class differentiable programming language, so that you're not only differentiating things that are available in TensorFlow or PyTorch, but that you can differentiate larger swaths of code, right? So that, if I have a tax optimization program I'm writing, maybe I can, optimize my tax calculation, for example, right? Or if I'm, designing, a new kind of a combustion mechanism for my rocket, I could do that with differentiable programming. So that's one thing.
So SciML. So these are people using ML in science.
Exactly.
So
exactly.
why didn't they use Python?
So so that's a very good question, actually, right?
And then if we can answer this, maybe we can figure out how to grow.
Absolutely. So the reason why many scientists and engineers do not use Python, I mean, everyone's learning Python today, and I'm sure they're trying it out, but a lot of their core workflows still tend to be in either C++, sometimes in MATLAB. And the reason is performance, right? Because when you're doing modeling, when you're doing simulation, performance matters. And they are unable to write, code in C++ on their own, right? They are not trained as programmers. They're trained to write mathematics, right? So using Julia, using MATLAB, using R, using Python, they can write at the level of mathematics, but only in Julia can they get the performance of C++. And now when you want to add machine learning to that mix, right? You don't want to throw it your 200 years of science that you have at your fingertips, right? You don't want to say, all right, Google has the flexibility and the ability to do this, right? They can say, I have 1 billion images from my whatever Google Images database, and I'm going to train machine learning on it, right? Or I have all this Android data of speech, and I can build a speech algorithm. That doesn't work if you're a pharmaceutical company, or
and also there's a presumption that everything is deep learning.
There is but deep, if you step back, what is deep learning, right? It's differentiable programming plus optimization.
No, but I mean, the scientists that you work with, not all of them, they have multiple.
They want to be able to combine, their data sets, which is not big data, right? It's like a clinical trial takes hundreds of millions of dollars to generate what would be a small database, right? Of what happened, in those patients and trials, right? So, what our users want, right, is the ability to work with data, the ability to bring in science and simulation, and the ability to apply machine learning in combination with science. Not, the view is, many of us computer scientists have the hubris that I don't care about the domain information. I have machine learning. I will just learn everything. Give me enough data.
This is a key insight, in the sense that, at some point, I think, when you're in industry, you're doing ML, and then you will hit a point where, okay, there's a point of diminishing returns with just pure ML. I have to combine ML with other things as you're describing, right?
Exactly, exactly.
Okay.
If you can bring your domain knowledge into the simulation, you can be immensely faster and immensely cheaper than anything else. And those are the people who are going to win, right? Is the people who can combine the best of all these different worlds as opposed to one or the other.
So what we need to do is somehow showcase some of these examples.
Yes.
And highlight, this is where yes, you can do pure ML, but look, if you're willing to not be dogmatic about it, you can be a lot more effective.
We've actually published a couple of papers on some of these topics where we show that if you use traditional machine learning on differential equations, it will actually get the physics wrong, right? Like mass will not be conserved in your equations if you use traditional machine learning. But if you use Julia SciML tools,
but if you have more data, that's what the ML people will say.
Or, yeah, just throw more data and more compute. We'll have more TPUs,
But so the SciML is a success story. So is there another subgroup within it that uses Julia for ML?
I mentioned the AlphaZero.jl. So there are researchers who are trying to apply reinforcement learning to other areas, and some of them are using Julia. So in this case, this is a group that's led by Carnegie Mellon, and this particular researcher is actually using it for theorem proving, for example, right? So they're bringing research, because Julia is so strong at math, it was the right system for them to sort of combine machine learning, reinforcement learning, and theorem proving all into one system.
And honestly, for our listeners, if you look at Julia code, if you can code in Python, I don't know that it's really that much different.
Oh, my guarantee is 1 week or your money back.
1 week and you get multiple dispatch, right?
That's right. multiple dispatch will blow your mind, right? Okay, let me just tell you that because chances are
so let me challenge you. Let me challenge you here, right? So explain multiple dispatch to in as plain language as possible, right?
Oh, so I will point out that there is a fantastic Ars Technica article written by sorry, the name.
So let me reframe. So multiple. Give the case for multiple dispatch to a non-technical person. What?
So here's
not or in as least technical language as possible, right? So
think of multiple dispatch as the generalization of object-oriented programming. Okay, so in object-oriented programming, you have an object, right, and then you dispatch methods on the object, and it's always on the type of the first object that you dispatch your methods on. So it's a single dispatch system. Simply put, in multiple dispatch, you pick a method based on the input types of all of the different arguments that are given to the function. So for example, I'll give you a very simple example. Let's take the function plus. Let me ask you a question, right? Just, you may already know the answer.
So in other words, so in multiple dispatch, you can have multiple definitions of a function.
Yes.
As long as each definition accepts different combination of
data types,
statically typed arguments, right?
Yes.
And then it's more than that, actually, because basically beyond that, then Julia actually can take your multiple functions and somehow it's blazing fast.
So this is the real design innovation in Julia that makes it fast, right? Because the language designer gave you, the user, the system of multiple dispatch, you are now writing all these different functions where they take, the same function is taking different types and then does something differently, right? Like if I want to add 2 integers versus 2 floating point values versus 2 dates, right? In Julia, you would write these as little functions, like little 3-line functions separately. And now the compiler, when it's doing its type inference, it just has to look up this table. Oh, if I have, two dates, then I just need to call the function with the two dates. I don't need to worry about the 300 other definitions of plus. I can pull that in, and then I can compile it to the absolute minimum tight assembly. And this is one of those few language features which gives everyone something, right? So, sometimes you have language features that are only good for the designer, and sometimes they're only good for the user. You rarely find language features that are good for both.
Now, let me put you on the spot here. When you folks decided to implement this particular feature, multiple dispatch, what impact and how were you expecting this level of excitement and impact, or was it just like one of these programming language discussions for, yeah, that would be cool, but yeah.
That's how we started. We had some early intuition into building, from prior experience, that this is possibly a good idea. In fact, I have my email with Jeff and Stefan and Alan from the very, very first days of the Julia project in 2009. In the first week of the project, Jeff asked, what do you guys think about multiple dispatch? And Stefan and I both chimed in and said, yes, we should do it. We think it's going to be really cool and impactful. But the real impact of what it would enable, is only to be seen today, right? Like when you look back. But back then it was a hypothesis, and we are just, really, really glad that it worked out. And back then we picked it because of necessity, right? Because there were only 3 of us in the first few years. We had to write all of these mathematical and scientific operators and all this data processing and this immense library. And Jeff was writing the compiler. Stefan and I had jobs, right? I mean, this was like literally our night and weekends thing. So we had to have a system that we could be extremely productive in and not lose any performance. And so it was that dynamic that led to the creation of a multiple dispatch based system. And it turned out to be really, really a good idea. And many academics have now gone back and analyzed, like, hey, this has been really successful. What about it actually worked? And what are the lessons to be taken?
So let's close the loop and go back to your Series A.
Mm-hmm.
So Series A means you're hiring. So this
Yes.
is your chance to describe to our listeners what you're looking for, what kind of positions, and why they should consider Julia Computing.
So, we are well funded, as you pointed out now, and our next task is to take Julia to millions of users through Julia Hub, which is our cloud platform. We're taking it to hundreds of companies with a focus on pharmaceutical companies right now. So we are looking for, of course, talented cloud engineers and architects who can come help build this large distributed, Julia Hub cloud system that works on all the clouds. The other major area of hiring is sales engineers. So if you're an engineer and if you've never worked with sales, but you're good at, communications, you're good at talking to people, please reach out to us. We are looking for folks who can work at the intersection of business and engineering, right? Heavily technical role, but where you are, getting things done at the customer location and getting some of these amazing SciML kinds of applications deployed into some of the largest and most complex use cases.
By the way, the side benefit, obviously, of your guys' focus is a lot of the projects are actually going to be high impact projects.
That is very important.
Pharmaceutical, healthcare, right? That kind of thing.
Yeah. We are right in the midst of a pandemic here, right? And we are doing our role. Climate science, right? Some of the biggest new climate codes are now written in Julia. So these are all high impact projects. Every single thing that we do is high impact and touches innovation that will, hopefully, impact all of our lives. And this is personally for me the most important thing about what I work on. And so, that's why we're slow and meticulous. We, carefully pick the team of people who share our values and our mission. And that's how we are building out the company.
And with that, thank you, Viral, and we'll check in again next year.
Thanks, Ben. Really exciting to talk to you as always.